In the last video, we looked at the titration curve for the titration of a weak base with a strong acid, and we found the pH at 2 points on our titration curve. We found the pH before we'd added any of our acid, so that was right here. We did that in part A of our question. In part B of our question, we found the pH after we'd added 20 milliliters of our acid, so that point is right here on our titration curve, and we found the pH in part B. In part C, our goal is to find the pH after we've added 40 milliliters of our 0.1 molar solution of HCl. So how many moles of acid did we add this time? So the concentration of HCl is equal to 0.1 molar, right? So that's equal to 0.1 molar. Molarity is moles over liters. So how many moles of acid did we add? Well, we added 40 milliliters, which if we move our decimal place 1, 2, 3, that's 0.04 liters. So we added 0.04 liters, and we could just solve for moles here. So the moles of HCl would be equal to 0.1 times 0.04. So 0.1 times 0.04 is equal to 0.004. So that's how many moles of HCl we have added. So you could think about this as H plus and Cl minus, and if you have 0.004 moles of HCl, that's how many moles of H plus you have too. Or you could think about H plus and H2O giving you H3O plus or hydronium. So you could also say 0.004 moles of H3O plus. All right, how many moles of ammonia did we start with? All right, well, our concentration was 0.1. So the concentration of ammonia that we started with was equal to 0.1 molar. And once again, molarity is moles over liters. We started with 40 milliliters of ammonia, which is 0.04 liters. So we started with 40 milliliters or 0.04 liters. So to find moles of ammonia, it's the same calculation we just did. 0.1 times 0.04 gives us 0.004 moles of ammonia, moles of NH3. So the acid that we added in our titration is going to react with the base that we started with. So let's go ahead and write out the neutralization reaction. So one way you could write that would be NH3 plus H3O plus. So ammonia, NH3 plus hydronium, H3O plus. So H3O plus is our acid, right? It donates a proton to ammonia. So if NH3 picks up a proton, it turns into NH4 plus. And if H3O plus donates a proton, we're left with H2O. So that's one way to represent our reaction. The other way we could write it would be NH3 plus HCl. So let's write it that way too. So ammonia plus HCl. Right? HCl donates a proton to NH3, giving us NH4 plus. And once HCl donates a proton, you have Cl minus, right? The chloride anion, the conjugate base. So this would be NH4 plus Cl minus. All right, let's write down how many moles of acid that we have. All right, so we added 0.004 moles of our acid. So let's write down 0.004 here for moles of acid that we added. And for moles of base that we started with, that's also equal to 0.004. Let's get some more room down here. So we started with 0.004 moles of our base. All right, if you look at your mole ratios there, right, so 1 to 1 mole ratio. So we have now added enough acid to completely react with the base that we originally had present, right? So this represents the equivalence point of our titration, right? This is the equivalence point for our titration because we've now added enough acid to completely react with our base, right? So all of this acid is going to react, right? So we use up all of that, and it uses up all of the base that we had present. So all of this base is going to react with the acid. We're going to lose all 0.004 moles of NH3. So we're left with 0 of that. Ammonia turns into ammonium, NH4 plus. And so if we start with 0 for NH4 plus, right, whatever we lose for ammonia was what we gain for NH4 plus. So if we're losing 0.004 moles of ammonia, that's how many moles of ammonium we are gaining. So we gain 0.004 moles of NH4 plus. So after we add the acid, right, we're left with 0.004 moles of NH4 plus. So this is at our equivalence point. So we have some ammonium present. What's the concentration of ammonium that we have present? Well, concentration, once again, is moles over liters. All right, so we have 0.004 moles of NH4 plus. So let's write 0.004 moles of NH4 plus. What is the volume, right? What's the total volume now? Well, let's go back up to the problem, right? We started with 40 milliliters of our, we started with 40 milliliters and we added another 40. So 40 plus 40 is 80 milliliters, or 3.08 liters. So our total volume now is 0.08 liters. So let's go ahead and write that in here. So 0.08 liters. So 0.004 divided by 0.08 is just equal to 0.05. Right? So 0.05 molar is the concentration of NH4 plus that is present. All right, ammonium. Ammonium is a weak acid. Ammonium can react with the water that is present. So let's now write out that reaction. So NH4 plus is going to react with the water, right? And ammonium is going to function as an acid. Ammonium donates a proton to water. So if NH4 plus donates a proton to H2O, H2O turns into H3O plus, or hydronium. And if you take away a proton from NH4 plus, you're left with NH3, or ammonia. So ammonium reacts with water, and that's going to affect your pH, right? If I go back up here, so NH4 plus does react with water, but the chloride anion does not react appreciably with water, so you don't have to worry about this being present. But the NH4 plus will affect the pH, which our goal, of course, is to figure out the pH. All right, so let's get some more room, and let's write in our initial concentration of NH4 plus, which is 0.05. So the initial concentration of NH4 plus is 0.05. And once again, for these problems, these weak acid equilibrium problems, we assume that we're starting with 0 for the concentration of our products. And our change, right, we're going to lose a certain concentration of ammonium. A certain concentration of ammonium is going to react with water. So we're going to lose X, right? And then whatever we lose for ammonium turns into ammonia. So if we lose X for the concentration of ammonium, that's the same concentration that we gain for NH3, for ammonia. Right? And therefore, that's also the same concentration of H3O plus. So at equilibrium, right, at equilibrium, we're going to have 0.05 minus X for the concentration of NH4 plus. For the concentration of H3O plus, we have X, and for the concentration of NH3, we also have X. All right, next, this is functioning as an acid, right? NH4 plus is donating a proton to water. So for the equilibrium expression, we have to write Ka here. Right? And Ka is equal to concentration of products over reactants. So we have concentration of H3O plus, which is X, times concentration of NH3, which is X, all over the concentration of NH4 plus, which is 0.05 minus X. So 0.05 minus X. All right, Ka for NH4 plus, right? Ka for ammonium, we calculated in an earlier video, and we found it to be 5.6 times 10 to the negative 10. So this is equal to X times X is X squared, and 0.05 minus X, if X is a very small concentration, 0.05 minus X is approximately the same as 0.05. So we write 0.05 in here to make our lives easier for the calculation. And we can get out the calculator and solve for X. 5.6 times 10 to the negative 10. Right, we're going to multiply that by 0.05, and then we're going to take the square root of our answer and solve for X. X is equal to 5.3 times 10 to the negative 6. So let's go ahead and write that down. X is equal to 5.3 times 10 to the negative 6. And we go back up here to see what X represents. X represents the concentration of hydronium ions, right, at equilibrium. So this would be the concentration of H3O+. We've done a lot of work, and the last thing we have to do is find the pH. And now we've found the concentration of hydronium ions. So the pH is just the negative log of what we just found. So negative log of 5.3 times 10 to the negative 6. Let's get out the calculator and do it. So we have the negative log of 5.3 times 10 to the negative 6, and we get a pH of 5.28 if we round that, right? So our pH is equal to 5.28. So at the equivalence point, our solution is acidic, right? A pH of 5.28. Let's find that on our titration curve here. So we've added 40 milliliters of our acid, and our pH is 5.28. So let's say that is 5.28 here. So this is part C of our question. The pH is equal to 5.28 at the equivalence point. Finally, in part D, our goal is to find the pH after we've added 60 milliliters of our 0.1 molar solution of HCl. So this time, how many moles of acid have we added? We can find that from the molarity, since our concentration is 0.1 molar, right, of HCl, and molarity is moles over liters. So we're adding 60 milliliters, which is 0.06 liters. So that's 0.06 liters. We solve for moles. 0.1 times 0.06 is equal to 0.006. So that's how many moles of HCl we've added now. Right, HCl is H plus and Cl minus, so you could think about this as being 0.006 moles of H plus, or add your proton onto water to form hydronium, H3O plus, so 0.006 moles of acid. Remember from part C, we needed 0.004 moles to completely react with the ammonia. So at this point, we're going to lose 0.004 moles because that much is necessary to react with our ammonia. So how much is left over? So after our acid has reacted with the ammonia, we're left with 0.002 moles of acid. So that's how much we have present in solution. So next, since our goal is to find the pH, we need to find the concentration of hydronium ions. So the concentration of hydronium ions would be equal to the moles, which is 0.002, right? And we need to divide that by our volume. Well, our volume would be 40 milliliters plus 60 milliliters, right, which would be 100 milliliters. So that's our total volume here. 100 milliliters would be 0.1 liters. So we have 0.1 liters here, and we can solve for the concentration of hydronium ions. So 0.002 divided by 0.1 gives us a concentration of hydronium equal to, this is 0.0200 molar. So now we're ready to find the pH. Since the pH is equal to the negative log of the concentration of hydronium. So the negative log of 0.0200, let's get out the calculator, is equal to, so the negative log of 0.0200 is equal to 1.699. So our pH here, our pH is equal to 1.699, or however you want to think about rounding these things. You could just say 1.70 just to make things a little bit easier to think about that number. So approximately 1.7 after we've added 60 milliliters of our acid. So on our titration curve, right, we've added 60 milliliters of acid. So here we are right here, right, and our pH is pretty close to 1.7. So we're past the equivalent point on our titration curve now.